In this video, we're going to do a proof of Lagrange's theorem, which is a theorem about finite groups and finite groups only. And what it tells you is that if you have a finite group G and a subgroup H of G, then the size of H divides the size of G. So you can see this doesn't make any sense for infinite groups. It's necessarily restricted to the case where G is a finite set. So before I do a proof, one of the main reasons this is useful is because it restricts what the possible subgroups of a given group are. So if you have a finite subgroup, a finite group G, and you're interested in what its subgroups are, Lagrange's theorem tells you that the only possible subgroups are sets with size which divides the size of G. So it's telling you something very special, especially about groups with a prime order. It's putting a very large restriction, very heavy restriction on the possible subgroups of a group whose order is a prime number. So let's begin with our proof. We will keep G as the name for our group, and we'll keep H as the name for a subgroup, and we're going to introduce a following relation on the group G. So we define a relation on G by X is related to Y if and only if there exists an element in little h and big H such that X equals Y times H. Now I claim this is an equivalence relation on G, so we're going to check the three parts of the definition of an equivalence relation. If you can't remember how that definition works, pause the video and look it up. So equivalence relations have three parts to their definition. The first one is reflexivity, and that says every element of G should be related to itself. Well, this is easy. X, whatever X is always equal to X times the identity. So for all X in G, X is related to X. Okay. The subgroup H must contain the identity because it's a subgroup, so the identity is in H, so we really have shown that every element X is related to itself. Okay, let's do symmetry. Let's let X be related to Y. So X being related to Y means there exists an element in the subgroup H with the property that X equals YH. Okay, now you can multiply both sides of this equation by the inverse H inverse, and if you do that, then what you get is X times H to the minus 1 is equal to Y. Y is equal to H times X to the H to the minus 1. But because H is a subgroup, H inverse is still in H. So look, you have Y equals X times, on the right, an element of the subgroup H, and so Y is related to X. We've done symmetry. Finally, we have to check transitivity. So let's suppose X is related to Y and Y is related to Z. So what that means is X is equal to Y times H and Y is equal to Z times K for some elements H and K of our subgroup K. Alright, let's now just substitute into this equation. X equals Y times H, Y is equal to Z times K. So substituting for Y, we get X is equal to Z times HK. Excuse me, Z times KH. Let's just bracket it just to be careful. We substituted ZK in place of Y there. And of course in a group, the group operation is associative. You can re-bracket it however you like. And I'm going to re-bracket this as K times H. But look, K and H were elements of a subgroup H. Subgroups are closed under multiplication. So KH is in H as H is a subgroup of G. So what have I got? X is equal to Z times, on the right, an element of the subgroup H. So by definition, X is related to Z. Okay, we checked all three of the definitions, all three parts of the definition of equivalence relation. So we get the result that this relation tilde is an equivalence relation. Okay, think back to all the things we proved about equivalence relations at the start of 0007. We proved that if you have an equivalence relation on a set G, then actually every element of G belongs to exactly one equivalence class. We phrased that by saying that the equivalence classes are a partition of G. And that means you can get the size of G by adding up the sizes of the equivalence classes. So what we're going to do then is we're just going to prove every single equivalence class has the size, the same size as the subgroup H. So we'll show if X is an element of G, then the equivalence class of X under our relation has size equal to the size of H. Okay, well, let's just think first, what is the equivalence class of X? It's the set of all things which are related to X under our relation. Something is related to X under our relation if it's equal to X times an element of H. You could move this H inverse over onto the left there, and you get exactly that the set of things related to X is the set of things which are equal to X times an element of H. Okay, now I know what my equivalence class looks like. Let's think what I've got to do. I have to show that this equivalence class has the same size as H. And if we want to show that two abstract sets have the same size, what we do is we write down a bijection between them. So let's write down bijection. Let's write down a bijection between this equivalence class and between the set H. So if we take a map from H to the equivalence class of X, given by f of H is x h. That is a function from the subgroup H to our equivalence class, and it's a bijection. And if you want to know why it's a bijection, you can check that it's a bijection by coming up with an inverse, and the inverse is G from the equivalence class to H given by, well, G of an element of our equivalence class, so let's just call that arbitrary element C, is going to be x to the minus 1 times C. So you should check that f composed with G is the identity function on our equivalence class, and G composed with F is the identity on H. When you've done that, you'll know that those two functions really are bijections. Therefore, the equivalence class has the same size as H, and that completes our proof, because now we can get the size of G by adding up the sizes of the equivalence classes, but the sizes of the equivalence classes are all the size of the subgroup H. So that means you get the size of G by adding up the size of H a lot of times. In other words, the size of G is a multiple of the size of H, which was what we required. Okay, we're done. That's Lagrange's theorem. And as I say, the real utility in Lagrange's theorem is that the fact that it puts a real restriction on the possible subgroups of a particular group. So if you were given a finite group G and you wanted to know all the subgroups, well, you now have a strong restriction on what the possible orders of subgroups of G are. The possible orders of subgroups are just the divisors of the order of G. So there's no guarantee that a subgroup exists with each possible order, but you do know that any subgroup will have order, a divisor of the order of G. Okay, let's now prove some corollaries of Lagrange's theorem, because actually it tells us quite a lot about the possible orders of elements of G as well. So here is our first corollary to Lagrange's theorem. It says that if G is a finite group and X is an element of G, then the order of that element divides the order of G. Okay, let's do our proof. What do we know about the order of X? We know that if we look at the subgroup generated by X, the cyclic subgroup generated by X, then the size of the cyclic subgroup generated by X is equal to the order of X. So this is a lemma we proved before. But Lagrange's theorem the size of any subgroup of G divides the order of G. So the cyclic subgroup generated by X, that's a subgroup of G, so the size of this divides the order of G. Okay, we're done, because this size of the cyclic subgroup generated by X is the order of X. So the order of X divides the size of G. Okay, proof over. We now know that the order of an element of a finite group divides the order of the group. And again, this is incredibly useful when you're trying to figure out the possible orders of elements of G. You know that in a finite group, the only possible orders are divisors of the order of the group. So you know for free, for example, that if you look at, let's say, S4 has, straight away that this has no element of order 5. Because if you look at the size of S4, you know the size of Sn is n factorial, so the size of S4 is 4 factorial, that's 24, and 5 is not a divisor of 24. Okay, so all kinds of useful things comes out of these corollaries to Lagrange's theorem, and if we move on again, we can get another corollary here, which is going to be useful to us. So this corollary says, this is a corollary to Lagrange's theorem. It says that if you have a finite group G and an element X of G, then if you raise X to the power size of G, then you must get the identity. Okay, let's do our proof. If we take the order of X, well, what does our last corollary tell us? Our previous corollary tells us that the order of X is a divisor of the size of the group. So what can we say? We can now write that the size of G is a multiple. Let's say it's K times O of X, where k is an integer, positive integer in fact. Okay, let's now work out x to the power mod g. Well, that's x to the power of O of x times k. I'm going to use my exponent laws. That's x to the O of x all to the power k by the exponent laws. Okay, what do I have there? X to the power of the order of x. Well, the order of x is defined to be the smallest power of x, smallest strictly positive power equal to the identity. So what you've got there is just the identity to the power k, and that's, of course, the identity. Okay, we're done.